Okay, there we go. Well, what we're going to do is, and I don't know where everybody's at. I'm going to have to figure that out. But we have our test on Friday. Now, yesterday when I told you that, that's okay. It's not till Friday. So what we're going to do is we're going to spend all day today with the article. We're going to spend half of tomorrow with the article. And then I'm going to start wrapping things up. And what I'm going to do is part of the day tomorrow, I'm going to explain some things we did in the past, kind of review for the test. And then Thursday, I'll do the same thing where we kind of review for the test a little bit. And I'm going to get you into groups on Thursday. So you're going to have about 20 minutes on Thursday where I'm going to get you in a group. And your goal is to, I'm going to give you a list of about 20 to 25 vocabulary words, science words. And you're going to sit at a table with some other people, and you're going to write out the story, the science of how a candle works. Okay? And that's what's going to happen on the test, too. So the test is the only test all year that's a little bit of this and a little bit of that. There's a little bit of chapter 1. So you took notes on chapter 1. Remember that? All right? We'll go over that before the test. And then there's demonstrations that we did. I'll go over those. I'll review those before. And then we had the candle lab. And I can't ask questions on the lab itself unless it had to do with safety. I could ask questions about that. But most of the questions had to do with this article here on how the candle works. So I know it seems strange. If I was in a class and normally have 15 here and there's only this many, it would seem kind of strange. But I do need to go ahead and have a regular class. So they can watch the video if they're not here today. And we're going to do some things. So anyway, the test will be on Friday. And then after that, we will start something completely different. And chapter 2 is... sometimes, for some people, it's the toughest chapter in the first quarter. For some, it's not. But it's actually based a lot on measurement and numbers and scientific notation and a lot about numbers. So if you're a numbers kind of person, you'll probably like chapter 2 quite a bit, like that. Any comments before we start? I feel weird that there's only this many of you here.
Will you give us a study guide?
Yes. So on Thursday, you'll get a piece of paper, and it'll actually say, it's front and back, it actually is a study guide for the test.
Should we get that earlier if you want?
Maybe. I might, I could print it, but on Thursday, that's what I'm going to do is actually go over it step by step. I'll see. Maybe I can print it tomorrow. How about that? All right, that's a good point. Everybody got that? If I can print it tomorrow, I'll give it to you tomorrow. All right, is everybody okay? Can you act like we have a full class? Can you act like it? Can you do that or not? Can you pretend? Okay, let's pretend. All right, let's go ahead and get your article out. And what I'm going to do is, let me turn the camera on. All right, first of all, let's review some things from yesterday. So who knows how many classes you were in today, but maybe you don't remember yesterday's lesson, but this article starts out with quite a bit of science, even on page 1. And I added some science, didn't I? So let's start out. One of the first things you see, not the first 3 paragraphs, that's just talking about the author himself when he was young and how he's very inquisitive. The first word is paraffin. All right, so since there's only this many of you, let's just everybody say something. Everybody's going to raise their hand, and anytime I ask you a question, you're going to answer one. You're going to answer one. What's paraffin? Go. Hydrocarbon. What else is it?
Wax.
So what? Wax. What else?
It's the most used wax for a candle.
It's the what? Yes, the most used wax on a candle. What's next?
Keeps the candle from burning.
It's what?
Keeps the candle from burning faster.
What kind of chemical? I didn't.
Candle, like, it's used in wax to keep it from melting faster.
Okay, are you talking about paraffin or stearin?
I'm just thinking the other thing.
Okay, so that's about stearin. Let's talk about paraffin a minute. What else do you know about paraffin? Leroy, what do you know? Is it an organic compound or inorganic? Organic. What's organic mean in chemistry? Carbon compound. What's hydrocarbon mean in chemistry? You only contain carbon and hydrogen, right? Okay. Now, We know also that paraffin is a hydrocarbon, and all hydrocarbons can burn. What does that mean in chemistry class? What does burn mean in chemistry? Yes, Libby.
Combining with oxygen in a chemical reaction.
Very good notes. Everybody got that? Anytime you hear that in chemistry, you know it's combining with oxygen in a chemical reaction. It's a chemical change, isn't it? Not a physical change. Good, great. But where's it getting the oxygen from? The air. How much of the air is oxygen?
20%.
Only about 20%. Is that right? So we figured out a lot of things already. Now that 20% is going to come into play in a minute when I ask you about, do you think the flame gets enough oxygen? Well, it must get enough to burn, but what if you gave it more oxygen? What if I put a candle in 100% oxygen? What do you think would happen? It would be brighter, and it would burn the candle faster. So anyway, all right, let's go back to stearin, okay? Sterin's another chemical, and I had a student email me. They're kind of, they must have been excited because they were looking on the internet. I told them to get them extra credit, but he wasn't here today. So he emailed last night, and it says, I found the person who discovered sterin, and I haven't got to see the article yet. I'm hoping it's going to say that somehow he found out it burned like a candle, and if you mix it with paraffin, I don't know. I'm hoping it's going to have the whole story there. Because how in the world did you think, put stearin with paraffin? What do you remember about adding stearin to paraffin? What does it do?
It lets the candle last longer, like it won't burn super fast.
How does it make it last longer?
It raises the melting point.
Raises the melting point. That means it takes more heat. It makes more time. The flame has to be on for a longer period of time before it can change from a solid to a liquid. So the candle will last longer, won't it? All right, let's look at the zones of the candle. What are the 3 zones of the candle? Keep answering. Dave, you want to give me a zone? You can look right here.
3 zones.
Yeah. What's one of them?
The yellow zone.
Of the flame.
The yellow zone.
I know they have a name for that. What's the yellow part? Now, I'm okay because we actually haven't read this yet. I gave you the names yesterday, but we're going to read about each one of these zones in just a minute. All right, Rita.
Luminous zone.
And luminous, it's the brightest part, isn't it? It is illuminating. What's another zone? Okay, and that's found right above the wick, isn't it? And another one. Pardon.
Reaction zone.
Now, the reaction zone is usually where the blue is, and it's along the edge here, isn't it? Like that. That's the reaction zone. All right, we also found out that there were different temperature zones of a candle flame, and there actually is a little bit of a pattern. It didn't have to be a pattern, but it seemed to be. At the wick was right about 600. Right above the wick was how much? 800. And right at the top of the dark zone was how much? 1,000. And then above that, in the luminous zone, what?
1,200.
1,200, right? Is that right? So it goes up by 200, doesn't it? And I would have thought that would have been the hottest part right there. But believe it or not, it's not there. Where is it?
In the middle.
It's right about here, and it's probably at the tip of the reaction zone, isn't it? So it seems to be right about here. And I don't know, somebody discovered that. I didn't. All right, also, they found out that the wick makes a difference. What did they do to a wick to make the candle even better than it was before? You know this?
They pickled
What's that fancy word?
it. They plated the cotton.
Right? No, plated means braided. That means they twisted it. But what's that fancy word that means they treated it with a chemical? Mordanted. I didn't, until I read this article about 30 years ago, I didn't know what that word was. Mordanted, and we call it pickling, right? And pickling simply means the chemical you put in is going to absorb that chemical and change its nature a little bit. Nobody has shown me that either. I don't know who did that first. Who decided, hey, if you do this to the wick, you make a better candle? Who knows why it made it a better candle? Why are candle wicks today pickled? Anybody remember? Yes.
It produces less smoke.
More smoke?
Pickled, less.
Oh, less. You're right.
Lessens the smoke.
So that means for a long, long time, if you bought a candle even if it had stearin in it, it probably gave off black smoke, didn't it? And then, wow, can you imagine a company who first came up with one that no black smoke? Man, I want that. Look at my ceiling. I burn candles all the time. Look at my ceiling. You know, not here, but I mean back then. Okay. Also, let's see here. It also said that if you pickled it, it would also make an ashless decomposition. So when that wick does burn, it used to always turn into an ash and probably fall into the candle. The candle probably got black from the ash and stuff like that. But this, did you ever see that? Did you ever see a little piece of your wick fall off? And not unless you knocked it off, right? So they made it, that also is another thing. All right, did we talk about the double boiler? Did we get this far? You would not ever want to heat paraffin in a pan on a gas stove just by itself. What would happen? What could bad happen? Say it again. How? How would it catch on fire? If I melted it, it would change from a solid to a liquid.
Wax with hydrocarbon because it doesn't mix with water.
Okay, so if I keep heating the liquid, what happens?
Turns into a gas.
Change to a gas, didn't it? And the gas comes out. And if the gas comes out and there's a flame source right there and there's a lot of air, there's going to be a big fireball, a big one. All right. They also said that some church candles were pure stearin. Why? Yes.
Because it burned for hours and hours. So
Yeah, you didn't have to change it very often, did you? And remember the extra credit I talked about? I thought I'd let you see this. This is a company who uses I'm not sure they use paraffin, but I do know that they don't put any stearin in. I know that. Let me go ahead and start that. Now, right now, only the wick is burning. When you first light a candle, do you know that? Only the wick is only the wick is burning. Uh-oh, here come the naughty girls. Now, what happened?
Mr. Boswell let us out late.
He did what?
He let us out late.
Like real late?
Yes. Yeah.
Okay, what you have to do is go to the office, and you got to tell them that you're not absent. I'm sorry. So go ahead, go to the office, and tell them you're not absent because I can't change it. Once I mark you absent, then you're absent. So I had no idea. Wow, he was really getting on a roll or something, wasn't
Yeah, well, we just, yeah.
he? Okay. Wait a minute. Did you have advisory?
Yeah, they're all in our same class.
What?
They have Mr. Boswell.
I know, but that's advisory.
Yeah.
Okay. Okay. All right. He must have some good advice for them today. Oh, I was on tape. I shouldn't say that. Sorry. Okay, sorry. Anyway, we're going to watch that for a little while. Do you notice how it's already dripping? And they did that. See how they cut the candle here? Now, remember the video you saw? Instead of a nice little bowl being formed, see, a regular candle like that, the heat goes around evenly, doesn't it? And makes a nice little bowl. And he said that was the beauty of the candle. Because then the liquid wax would sit right in that little bowl, wouldn't it? Well, what's the liquid wax doing here? It's not, there's no little bowl, is it? Anyway, so we'll let that run. I don't mind using that whole candle. We'll see how fast it goes. All right, let's go to the wick. What if you have, did we read about the wick yesterday?
Yes.
What if you have a too small of a wick for the candle? What happens? Yes?
It will make a weak flame and it might turn out.
All right. Yes. What happens if you have too big of a wick for your candle? Somebody hadn't answered one yet. Do you know? All right. Now I want to ask you. Here's a hard question. Why in the world would a too small of a wick give you a weak flame, and too big of a wick, wouldn't that be a really good flame? Why is it smoking? Do you have any ideas?
I guess because the too weak one would die out quickly because it doesn't have enough, I guess, width or strength in order for the
What-
fire, since the fires are really
Enough wick to do what?
to burn.
Okay. So is the wick burning?
Oh, I guess enough width to actually
What do you think? If you have a small wick, maybe it's not enough heat to melt the wax. What do you think? Then what about the big wick? Wouldn't it have plenty of heat to melt the wax? Why would you get a lot of smoke? And I'm not expecting to know the answer yet. You will by the end of the day. By the end of the day, you'll know those answers. You get it? Yes.
Would it have like too much heat? And then it
What does that mean, though? Why was too much heat? Why would that be bad?
It wouldn't have enough. There would be too much heat to like be used on the wax alone
What does it be used for?
to melt the wax.
So you'd have a lot of heat to melt the wax, wouldn't you? Wouldn't that give you a lot of melted wax?
I guess.
Anyway, by the end of the day, you'll know how to answer that question, okay? Let's go on down. Did we read about Faraday? Did we read this paragraph? Okay. Anyway, so what I thought was amazing is, and I will ask you on the test about when did Faraday do these experiments, okay? He gave the lectures 1860, 1861. So somewhere around 1850, he would have done something in 1850, 1860. Is that correct? So at least you know, I won't ask the exact date. You get that? I might say 1650s, 1750, 1850, 1950. See that? And you know it's 1850, right? Everybody know that when this happened? Okay. Anyway, I thought it was amazing. They said, even today, there are parts of the candle we don't understand. Not a whole lot more is known about the candle than when Faraday did it. Wow, that's a long time ago. Wait. Oh, there they are. So your whole class went down there?
Yes.
Wow. How, I'm sorry this is on tape. The advisory teacher helped? Did somebody steal somebody? No, what happened? I'm just kidding. Why would the advisory keep you that long? Did somebody say something bad? No.
No, you're just like writing, and then you're just kind of sitting there, like no one like told us to do, so we're all just kind of sitting there.
So you guys weren't talking about something?
Oh, we're talking, but like we're doing homework and stuff, but no one like told us to leave, so we're all just kind of.
Okay. All right. Well, maybe somebody else. All right. What we're doing is we're reviewing. So far, we reviewed everything we did yesterday, and here's where the actual story starts. If you had to tell somebody how this works, besides telling them what a hydrocarbon is, all that, you would say the heat from the wick does what? What's the first thing you're going to say? The heat from the wick does what? Melts the wax. It changes from a solid to a liquid. Then what? Yes.
The capillary attraction happens.
Okay. What's that mean?
That the attracted molecular forces between the wax molecules and the wick molecules pull the wax upward.
What's it say in your own words? What does that mean in your own words?
It says that the
Okay, that's why I said this, right? And did I start the demonstration with you yesterday?
yes.
Okay, so I'm gonna start them again. Okay, just in case. I have some demonstrations that have to do with what he was talking about. This capillary attraction. Some of his books say capillary action. Same thing. Capillarity. Same thing. Everybody get it? That's a neat word. You should know it. You should know capillary attraction. Capillary attraction has two parts to it. There's the adhesion part and the cohesion part. What's adhesion? It's when different materials attract each other. What's cohesion? When the same material attracts itself. Now, I used to get those confused, so I came up with a memory trick. What was my memory trick? The first two letters of this word, ready? If the materials are different. Ooh, look at that. If the materials are different, then it's adhesion. Like if I put a piece of tape on a table and it sticks, what does that mean? Is that adhesion or cohesion? Adhesion. Right? They even call some Band-Aids, don't they call them adhesive Band-Aids? Adhesive tape? Oh, I get it. What's cohesion?
It's the same between materials together.
So what if water attracts water? As cohesion, right? So let's try it again, and I'll just repeat. I know I did one of those yesterday, but I didn't do them all. That's not blood. Somebody thought that was blood. This is actually food coloring. Okay, that's not blood. So what I'm gonna do is I'm gonna take a little tube, this little straw made out of glass is called a capillary tube. Have any of you ever gone to a doctor and they pricked your finger and put a little glass tube or plastic tube next to it? Did you ever see the blood shoot up in there? Whoa, what was magic? Not magic. What is it?
Adhesion.
Capillary attraction, isn't it? And so what we have here, watch. I'll just touch this thing. I won't not sucking on the straw. I'm just going to touch it. What happens? You see that? So what's happening is there's an attraction between the water and the glass, right? The water's attracting the glass, yes? But then the water attracts itself, so it pulls the rest of the water with it, doesn't it? Adhesion, cohesion, adhesion, cohesion, adhesion, cohesion. When you, especially next chapter, when you learn how to read a graduated cylinder, did they do that in middle school? They tell you about this little bulge. They call it a meniscus. Did you remember that name?
Yes.
You read the bottom of the meniscus. Well, why do we even have a meniscus? Nobody told me that. Well, because the edge of the water is in contact with the glass, isn't it? So the glass actually pulls the edge, what? It pulls it up. And then this water that's up higher is pulling the other water and makes it a little bowl, doesn't it? Because the water in the middle is not next to the glass, is it? Oh, I never thought about that. Everybody got that? All right, yes.
I need one of those packets with information. So
Oh, okay. Sorry. Also, if you want to watch like yesterday's video, I did review it. You weren't here, but if you watch yesterday's video with that packet with you, then you won't miss. You didn't miss anything. All right, now, even though you may or may not be impressed, let's say you are or not impressed. Okay, what does a glass tube have to do with the wick having capillary attraction? There's no. What are you talking about? There's no glass tubes in a wick. You're right, there's not. But there are no glass tubes in this piece of tissue either. Let me put that next to it. I mean, that almost looks like a cartoon. But why did that liquid shoot its way up into that tissue? What's that word? Capillary attraction, isn't it? Adhesion, cohesion. Let's do another one. Let's try one where I put two capillary tubes next to each other, but now I'm not going to put anything in the tube. I'm not going to put anything in the center of the tube. I'm going to lay it on the outside of the tube. I'll lay it between the two tubes. It's almost like a little motor, isn't it? But there's no motor, is there? Is there a motor? Anyway, this is a pretty scientific thing. It happens a lot. Yes?
what would be an example of cohesion?
All right. The glass is attracting the water, but then the water is attracting the water right behind it. So if I get attracted and I'm attracting you, then I pull you along with me, don't I? That's a great question. I'm going to try something I've never done. All right, I'm going to do this. Let me get this guy out of the way. That's why my fingers are red. I've been messing with this today. All right, let's try something. I'm going to try to make, I'm not going to have any kind of capillary tube, and I'm not going to have fibers either. There are no fibers. Let me see if I can spread that out a little bit. I don't want it to be too thick. Okay, let's try it. Ready? What's this? This is salt. This is like just grains. This is like grains. What happens? Go down here along the edge. See it move? And it's moving between one grain and another, isn't it? I don't even have to have fibers. You ever been to the beach? You ever think about that? You ever think about how water moves through the sand? You ever seen that? Anyway, That's capillary attraction. So that's something you should stay in your mind for a long time. Let me get rid of that. All right, let's move on, and let's go to the next part of the article. It said here that once the wax climbs near the top of the wick, what does it do? It changed from a solid to a liquid, and then the liquid's drawn up the wick by capillary attraction. Why? What happens then? What happens to the liquid wax? Yes?
Vaporizes.
Vaporize. It changes to a gas. It changes to a gas. And it has to get hot enough to change to a gas, doesn't it? And it says here, releasing hydrocarbon molecules playing a variety of roles. Now, let's read the next one. I need somebody to read this. Go ahead and read this paragraph. Somebody volunteer. All right, go ahead, Carter. The flame.
The flame has the interesting features I noticed as a child. Just above the wick, you see the dark cone that is topped by the yellow region responsible for most of the light. On the sides of the flame, near to the wick, are the blue regions. Depending on the diameter of the wick and the height of the flame, the blue regions may be only a fraction of the height of the flame, or may reach nearly to the top of the yellow region. It is surprising that the vaporized fuel molecules give rise to these three distinct regions instead of a single region of uniform flow.
All right, one more paragraph.
In the modern classification of flames, the type of flame produced by a candle is called diffusion flame. Another familiar type is called premixed flame. Its commonest examples are seen in the Bunsen burner and the gas stove. In the diffusion flame, the rate of combustion is determined by the rate at which the gases diffuse through each other, whereas in premixed flames, the gases are mixed prior to the burning, and the rate of combustion depends on the flow rate. For example, stove gas is mixed with air before it reaches the burner outlets. Further classifications of flames include the possibility of turbulence, but here I consider only a non-turbulent diffusion flame.
All right, here we go. Let's do some science. He says, when you vaporize a fuel and you burn it, why would this lead to 3 different zones of a flame? Why wouldn't you just read one kind of flame? It's fuel being burned, isn't it? Why? And we're going to learn that. And he says there's 2 kinds of flames. And diffusion flame, and what's the other one?
Premixed.
Okay, now how many of you have you have a gas stove at home, you've seen a gas stove, you know what it looks like at somebody else's house? Raise your hand if you've seen a gas stove work. Now raise your hand if you haven't. You have?
I have.
Okay, what does it look like? What's the flame look like? It's blue. Like a candle? Maybe part of a candle, right? But what about a fire in the fireplace? Diffusion or pre-mixed? The gas stove is pre-mixed.
It's diffusion.
Right. In a gas stove, the fuel is actually mixed with a certain amount of air, and it has the right mixture, and when you burn it, it all burns and you get one color flame. But a diffusion flame, we don't get one color. That has something to do with the oxygen, doesn't it? It has something to do with the availability of oxygen. All right. Excuse me. So, we did this experiment one other time. Let's try something here. Oh, I got to change the screen. Let that light for a minute. All right. So right now, this wick is melting this and forming liquid wax. Liquid wax is climbing up the wick by capillary attraction. When it gets hotter and hotter, all right, it changes from a liquid to a what? And gases are less dense than air, so they go up. Do you ever wonder why the flame is always up? It does. And that, you know why it rises? It's less dense. It's less dense than this air, isn't it? Do you know what a candle looks like if you're orbiting the Earth? Now, I'm not here to be your physics teacher, but I will tell you that they call that zero G in quotes, or microgravity in quotes. But when you're in orbit, the astronauts kind of look like they're floating, doesn't it? Again, I'm not here to teach physics. They're not really floating. It looks like they're floating. They're actually falling.
Attention athletics students, if you are participating in basketball workouts, they have been canceled today after school, but please come by Coach Clifford's office after school today. Thank you.
Okay, so we have a whole bunch of vaporized candle that's rising. Is that correct? Why isn't this thing blue though, like in a gas stove?
It's not pre-mixed flame.
Okay, so pre-mix means I'm going to have plenty of oxygen for every one of those molecules of fuel. You get it? You're all going to have enough oxygen to chemically react. Do you think I have enough oxygen here? No. So let me show you this dark zone. I did this before. This is a glass eyedropper. I'm going to take stuff from right in the dark zone, and I take it out and push it back into flame. What can you tell me about the stuff that's in that dark zone? Does it burn?
Yes.
It does. So there's fuel there, isn't there? There's fuel in the dark zone. You think it's being burned there? What do you think?
I think it's being
If it is, not very much, because I just took all the fuel out of here and I burned it, didn't I? So I actually, if it's already being burned, then I shouldn't be able to do anything. I shouldn't be able to do that. So there's fuel there, isn't it? Okay, now let's go on up. And so what happens here? It says so a campfire or a fire in a fireplace is diffusion flame. Okay, do you remember ninth grade biology? Okay, diffusion is the movement of molecules or chemicals from areas of higher concentration to lower. As soon as I light that flame, it uses up the oxygen right away, right next to it, doesn't it? That means that's no oxygen there. What does this oxygen do here? Higher, lower. Now, how does it get there? By bouncing. All right, I'm getting there. And it bounces both ways, but more of it bounces in than out. And it goes from areas of higher to, but how fast can it do it? How fast can it diffuse in? Only as fast as the molecules will bounce around. You get that? Is that fast enough to have enough oxygen for all that fuel? No. Let's take a look at the yellow part. Look at the yellow part of the flame. Did you ever ask yourself, why do I see that yellow flame? Isn't that the most obvious part about the candle? What makes, I don't see that in a gas stove. Why do I see a yellow flame here? Let's take a look. Now when I put that in there, what do you see happening? What is that? What is that? Did you guys notice that when you did the experiment? What is that? I'll give you a clue. It's black. It makes marks on a paper. It's actually the same material that you find in here, almost the same. And it's one of the elements on the periodic table. What is it? What? What is this black stuff?
Is it 10?
What?
Is it 10?
Say it again.
10?
Say it again.
10?
I can't hear.
10. She said 10.
Say it again.
10. T-I-N.
Oh. Carbon.
What?
This is carbon, isn't it?
I don't know.
You know what's in pencils? No. Now, they've never made pencils with lead, but we call it pencil lead, don't we? You know what's in it? Carbon. But anyway, all right. Hey, did anybody have any of their lunch they didn't eat? Anybody have any piece of lunch they didn't eat? Oh, that'd be a good teachable moment. What do I have in the freezer? Oh, I don't have anything. Nobody has any lunch left over? Okay. Let me see what I can come up with. What's that black stuff? What is it? Carbon. Think food made of carbon? When you took 9th grade biology, there were 4 major groups of organic compounds that you had to learn. Carbohydrates, do they have carbon in them? Yeah, they have carbon, hydrogen, oxygen. You had proteins, do they have carbon in them? Yes, carbon, hydrogen, oxygen, nitrogen. You had lipids, do they have carbon in them? Carbon, hydrogen, a little bit of oxygen. Nucleic acids, they have carbon in them? Carbon, hydrogen, oxygen, nitrogen, phosphorus. You get that? That's why you study them. They're called organic, didn't they? And so if I take any of those materials and I break them down chemically, what should I find? Right, if I took a green bean and put it in here and cooked it, I cooked it a lot, it would be black, wouldn't it? Is there carbon in green beans?
Yes.
There is. Ooh, I've never done that before. Okay, well, anyway, what's in that yellow flame right there? Carbon. Now, I don't see it. I don't see it. The only time I saw it was when I did this. I did something to that flame, and I see carbon. But I don't see carbon here.
Yo, Caldwell, we still have a volleyball game, so tonight's theme for that will be blackout.
Oh. That's it. All right, this is crucial, okay? This is kind of crucial. Now, I'm going to tell you something. Do you know why I don't see any carbon here right now? When it gets hotter and hotter and hotter, the carbon will react with oxygen and form, somebody said it a while ago. What compound would you form if you had carbon and oxygen? Yes. And so I don't see carbon dioxide. So when it gets hotter, when these pieces of carbon get hotter and hotter and hotter, then they turn to carbon dioxide. But what if I interrupt them before they get hot enough? Then what are they? What is it? Carbon. They weren't hot enough yet to form carbon dioxide with oxygen, did they? The other thing, I'm surprised that some of you did this, you didn't understand it, but I'm going to do this one more time. When you do that, and it gets all foggy, a lot of you said it was condensation. What's condensation? Water. I ain't putting water in this thing. Where's the water coming from? And let's think about this. Hydrocarbons are what? They're made of what chemicals? Carbon and what? And what's in the air? All right, if you combine that and that, what do you get? What if you combine that and that? Water. The water's coming from the hydrocarbons? Yes. Now, it's actually even more complicated because there are other things that are being formed there, but we have enough time, maybe one more minute here. By the way, did you notice what happened? I lit this at the beginning of the period. Your candle didn't burn that fast, did it? This candle was about this tall. And look at it. Now again, the whole purpose of them making this was to make an art. Ooh, this thing stuck to the table. Was to make something that looked nice. And so I could put another candle there tomorrow, a different color, and make it go this way, and I have a really pretty looking bottle, wouldn't I? But they purposely did that. They made their candle do what they wanted it to do there. I think I might put that out. There you go. Okay, there you go. All right. All right, what do you think? Do you understand it a little bit more? What I need to do is I only have half of tomorrow. So in half of days tomorrow, I'm gonna finish the story of how the candle works. Then we're gonna start our test review where I kind of fill in some of the gaps. I didn't even tell you what BTB was it. So we're gonna go all over since the beginning of the year. And again, I'll try to print that by tomorrow, the study guide, even though I probably won't use it till Thursday like that. All right, well, anyway, thank you very much. If you were here a little bit late, you can watch the video. Let me stop that.